Right. Good morning, everyone. My name is Luke Foye, and together with my thesis partners, John Feleciano and William Tyler Zylinski, we'll be presenting our thesis titled The Development of a Modern Hull Form Series in the Robinson Model Basin. Before we begin, we would like to thank several individuals who have made this thesis possible. Professor Golden, our principal advisor, for his knowledge in the commercial sector and his industry connections. Professor Royce, our reader, for his expertise of the web testing facilities and his aid in model fabrication. Professor Lutz, our editor, for his aid in communicating our results in the written document. Additionally, Professor Onus for his support in the preliminary seakeeping study. And Mr. Patrick Doherty for his support testing the model. The outline for today's presentation is as follows. We'll begin with the background of container ships, hull form series, and previous work. I will then state the objectives of this thesis project and describe the theory behind it. John will then cover the procedure of hull form development and seakeeping before Tyler explains the model making, testing, and results, then makes recommendations for future work. Container ships have been steadily growing in size since the advent of the shipping container, with the SS Ideal X having a capacity of just 58 boxes in 1956. Since then, port and global infrastructure have been continuously optimized for container trades, with ships being a large piece of this puzzle. The approximately cubic relationship between main particulars and capacity has engaged the economies of scale, with the largest ships, like the Evergreen Everace, exceeding 24,000 TEU in recent years. The exponential growth of large container ship capacity is seen on this graphic. The most recent 24,000 TEU vessels sit at 400 meters in length, 61 meters in breadth, and 16 meters of draft. Stepwise growth of container capacity is due to the additions of bays or rows rather than individual containers. The subject of this thesis is the second from the bottom, the ultra-large container ship, or ULCS. The most recent ultra-large container ship hull forms have distinct features featuring vertical stems, implicit bulbous bows, increased bow flare, and stern bulbs, all of which contribute to their efficiency and resistance profiles. All of these features are exhibited by the Evergreen Everace, the 24,000 TEU container ship launched in 2021, pictured behind me. To understand these design choices, a new hull form series will investigate the impact of this hull form with varying drafts, trims, speeds, and sea states. Shown here is a cross-sectional view of the wave terrain at the bow. Highlighted in yellow is the wave created by the high-pressure region imparted on the free surface by the ship's motion through the water. Now compare that previous waveform to the waveform of the bulb, highlighted in yellow now. Notice how they are out of phase. The bulb creates a wave ahead of the ship, which ultimately combines with the bow wave to result in a reduced wave elevation along the hull, highlighted in green. Less wave elevation means less energy imparted into the water, leading to reduced residuary resistance and fuel savings. However, traditional protruding bulbs are designed for a specific speed and draft and can prove detrimental at lower speeds or later drafts. The addition of a vertical stem, like the one shown on the left, compared to a traditional bulb on the right, has shown improvements to the vessel's performance away from the still water, full load draft design speed condition. Several recent studies have aimed to quantify this, with Wang et al. In 2021 examining the difference between a traditional protruding bulbous bow and an invisible bulbous bow on a cruise ship hull form, and Chen et al. In 2023 examining the addition of a vertical stem on a CRISO or KCS container ship. Both studies found that vertical stems with implicit bulbs offer efficiency over a greater range of speeds and drafts. The exact impact of this design would have to be applied across a specific operational profile to quantify fuel savings. Despite these CFD studies, there is still limited publicly available data on the resistance effects of implicit bulbs with vertical stems. At the same time that container carrier usage has grown, ships designed with high sailing speeds of 20 to 25 knots have operated well below their specific design speeds. This is due to emission pressures like the EEXI and CII metrics, terminal logistics, and oversupply of fleet capacity. This has caused a reassessment of hull form optimization when applied to large container trades. This is further exemplified by the graph, which shows the volatility of container ship sailing speeds and the overall reduction in the past decade. The first and most widely recognized systematic series, Admiral David Taylor's Series 60, analyzed a range of main geometric parameters, including the block coefficient, length to beam ratio, and beam to draft ratio, and the position of the longitudinal center of buoyancy, or LCB. This was through the creation of approximately 135 unique hull forms. Systematic series in the last century include the Series 60, the Marad series, the BSRA series, and the Taylor series. However, new developments such as bulbous bows, transom sterns, and stern bulbs have led modern container ships to deviate even farther from the Series 60. Several notable systematic series are shown in the table, where the green highlighting demonstrates the characteristics that ULCSs match. Adding the Webb ULCS parent hull, we can see that it does match the ULCS ratios and can be used to study the overall and detailed design features of the ULCS class. In 1961, Hun Chol Kim studied the addition of implicit bulbous bows onto an existing Series 60 at the University of Michigan. Using interchangeable bows on a 12-foot model, the block coefficient was kept constant as volume was pulled from the shoulder to the bulb to increase the sectional area from 0 to 3, 6, and 9% of midship sectional area in subsequent models. The results showed that larger bulbs had lower wave-making resistance at high speeds, while the smaller bulbs had lower wave-making resistance at lower speeds. Despite the promising results of this study, Kim noted that the newly introduced protruding bulbs, or Inouye bulbs, showed more promise and research should be concentrated there. Given the work that has been completed, the objective of our thesis is as follows. It is to lay the foundation for a new systematic series that more accurately represents modern ULCS hull forms than existing systematic series. Moving on to the theory behind ship resistance. Total ship resistance, R sub T, is made up of two primary components. The first is frictional resistance, R sub F, which represents the skin friction over the wetted surface area of the ship, computed empirically from the Hughes flat plate friction line, as suggested by the International Towing Tank Conference of 1957, or ITTC 1957. The second component is residuary resistance, R sub R, which compiles the wave-making, wave-breaking, spray, appendage, and form resistance. Since much of the current understanding of ship resistance is based on model testing, it is acceptable to quantify resistance as non-dimensional parameters, where the resistance term is decomposed by dividing resistance R by the density of water rho, the wetted surface area of the vessel S, and the vessel speed V squared. The non-dimensional parameters maintain the same relationship as the resistance components mentioned previously. Moving to the model scale, the total resistance of the model, C sub Tm, can be determined using the transformation on the previous slide. The model frictional resistance coefficient can be expressed as the logarithmic function of the Reynolds number of model, calculated from the ITTC 1957 correlation line. With the measured total resistance coefficient, C sub Tm, and the calculated frictional resistance coefficient, C sub Fm, the residuary coefficient is then calculated as the difference between the total resistance coefficient and the frictional resistance coefficient. Scaling resistance up to the ship, only the previously determined residuary resistance coefficient is equivalent to that of the ship. The frictional resistance coefficient of the ship must be recalculated using the ship's Reynolds number inputted into the ITTC 1957 correlation line. Finally, the total resistance coefficient of the ship may be determined as a summation of the frictional and residuary coefficients, along with the correlation allowance C sub A, which is specific to the test facility and size of the vessel. Matching the geometric conditions is necessary to accurately model the hull's resistance. To match geometric similarity, the linear scale ratio, lambda, must be satisfied. Thereby, the ratio between the ship and model's length, beam, and draft is constant. In the Webb ULCS series case, the length of the first models are the Robinson model Basin's standard model length of 5 feet, and the design vessel's length of 1,273 feet. The linear scale ratio is therefore 254.59. The linear scale ratio is then applied to either of two resistance scaling methods. Reynolds number scaling matches viscous forces and results in high testing speeds that are unrealistic in the Robinson model basin, say 6,600 knots for our model to match a full-scale speed of 26 knots. Froude number scaling matches gravitational and inertial forces and results in realistic testing speeds. So for the purpose of this thesis, Froude number scaling was used. The model speeds are therefore the ship's velocity, v sub s, divided by the square root of the scale factor lambda. I will now hand the presentation over to John to speak on the procedure of whole form development and seakeeping analysis.
Thank you, Luke, for going over the background and theory of this project. To begin our procedure, an initial or parent whole form was needed as the starting point. Next, that whole form was refined to better match our design requirements, and a seakeeping analysis was performed. Once the whole was refined and validated, the model was fabricated and a test matrix developed. Lastly, the model was tested in the tank and the data was analyzed. To begin our systematic series, an initial parent whole form was needed. Like any good engineering project, the first step was to clearly define the design requirements for this parent whole form. The previously mentioned ULCS characteristics, most importantly the vertical stem, implicit bulb, and stern bulb, must be features of the parent whole. Additionally, the full-scale size of the parent whole had to be determined. A commercial container ship operator was consulted and suggested a size of 16,000 TEU. In their experience, larger vessels face issues with port logistics, making the 16,000 TEU size optimal. This whole model must also be amenable to modification for future iterations of the series and producible with the materials and equipment available at Webb. For this thesis, 15-pound per cubic foot modeling foam cut with the Shopbot CNC machine were the available resources to create the model. Once our design requirements were identified, the American Bureau of Shipping, or ABS, graciously provided us with a whole form from their parametric database. This whole form matches the dimensions of a typical 16,000 TEU container ship and has all the characteristics of a ULCS whole form mentioned previously. Since this whole form comes from a parametric database, no intellectual property restrictions exist, and the lines can be made available to the public. This whole model is comprised of several surfaces joined together to produce a complete whole, with the black lines representing the edges of each surface. Shown here is the table of particulars for the parent whole form received from ABS. Based on the 16,000 TEU container capacity, the resultant model had a length overall of 388 meters, a beam of 57 meters, and a design draft of 16 meters. The displacement of this vessel at its design draft was 251,000 metric tons, with a block coefficient of 0.692. These parameters will serve as the starting point for the systematic series. Once the parent whole model was received from ABS, the next step was to perform a check of seakeeping characteristics to ensure that the whole has no adverse responses. Since this vessel is purely hypothetical, no data exists for the viability of the whole, so these characteristics must be verified computationally. For the parent whole form, a seakeeping study was carried out using DNV's Hydro-D WASM software, which uses a Rankine panel method transformed into the frequency domain. The Hydro-D model was first validated with first principle tests for roll and displacement before carrying out the rest of the frequency domain study. The environment used was a Brett-Schneider wave spectrum applied from sea states 5 to 8, which both limited the computational time and stayed within the linear region. The results were then compared to industry standards, with several being stricter than necessary to aid in visualization. 4 response characteristics were recorded on the whole: vertical acceleration at the bridge, horizontal acceleration at the bridge, vertical acceleration at the forward perpendicular, and roll amplitude. These 4 gave a clear picture of the whole's motion in the 6th degree of freedom domain. From the results of the seakeeping study, the motions calculated were not out of the ordinary for a 388-meter ship. The results are split into 48 polar plots like the one shown. Each polar plot shows one of the vessel's 4 response variables at a singular sea state and loading condition for all operating speeds and headings. The angle denotes the vessel's heading, 180 degrees is head seas. The radius denotes the vessel's speed, and the black values denote the RMS value at each operating point. This plot shows RMS values of roll amplitude. The color scale then shows the responses up to 25% over the given response limit, with blue values representing values under the response limit, white values at the response limit, and pink values being over the response limit. As the seakeeping analysis was being performed, work began to refine the hull form into a singular surface. A model consisting of several hull surfaces joined together is difficult to modify, so Rhino 3D was used to create the hull as one lofted surface. This redeveloped hull was modeled with a tolerance of plus minus 1% of beam, or 570 millimeters in the transverse direction. After the new hull surface was lofted and faired, the final result closely matched the original parameters of the ABS hull. This remodeled hull preserves typical ULCS characteristics and is easily modifiable to support future variations of this thesis. All particulars match within 1%. The differences between the original ABS parametric hull and the remodeled parent hull lie in the surface definition, shown on this slide. Note the lack of seams on the remodeled hull surface, showing that it is continuously defined and more amenable to modification. To facilitate the creation of a useful systematic series, numerically describing complex hull geometry is essential. While industry standard parameters exist for protruding bulbs, no such parameters were found for implicit bulbs or stern bulbs. To accomplish the objectives of this thesis, novel parameters were developed to describe these characteristic ULCS features. The first parameter developed for the implicit bulb was sectional area at station 0.5 from baseline to design waterline, given the variable name A sub IB. This parameter was inspired by Kim's 1961 work on implicit bulbs. The next parameter developed was maximum bulb breadth, B sub IB. Lastly, the height of maximum breadth was denoted H sub IB. These 3 parameters were selected to express the bulb's size and shape most efficiently, reducing the number of variables included in the series. To make these parameters applicable to hulls of all sizes, they were non-dimensionalized using another hull parameter. Bulb area was divided by midship section area to give C sub AIB, maximum bulb breadth was divided by beam to give C sub BIB, and height of maximum bulb breadth was divided by design draft to give C sub HIB. Figure shown displays the section taken for area measurement in red and the point of maximum breadth marked with a black text dot. Similar parameters were developed for the stern. The area at station 19 from baseline to design waterline was denoted as A sub SB. The maximum stern bulb breadth was denoted as B sub SB. And finally, the height of maximum stern bulb breadth was denoted as H sub SB. These parameters were non-dimensionalized in a similar fashion, dividing stern bulb area by midship section area to give C sub ASB, the maximum stern bulb breadth by the vessel beam to give C sub BSB, and the height of maximum breadth by the design draft to give C sub HSB. The figure above illustrates these parameters graphically, with the red line showing the plane that sectional area was taken from at station 19, and the black text dot showing the location of maximum stern bulb breadth. Because of the increased complexity in the geometry at the stern compared to the bow, 2 additional parameters were devised to fully characterize the whole shape. These parameters describe the transom height, denoted H sub T, and the aperture depth, denoted D sub A. The aperture is the cutout forward of the propeller, and its depth has a significant impact on propeller inflow. These additional parameters were non-dimensionalized by dividing transom height by design draft to give C sub HT, and by dividing aperture depth by LBP to give C sub DA. The figure shows these parameters graphically as dimension lines. After the parent hull was developed and characterized, the next step was to determine cut locations for interchangeable bow and stern sections. These locations were determined by analyzing the maximum extents of geometric change for extreme modifications to the bow and stern. It was determined that station 3 for the bow and station 16 for the stern were the optimal cut locations, allowing for variations of the respective section while preserving continuity and fairness across the joint. These interchangeable sections allow different bows and sterns to be tested without having to build a completely new model. The final step in our model development process was to create a naming convention for future iterations of the series. Each completed hull will be referred to by 3 numbers, with the first number referencing the bow, the second number referencing the mid-body, and the third referencing the stern. Individually, bows will be referred to by 2 numbers, with the first referencing the sequential bow number and the second referencing the mid-body it matches. For mid-body 1, bows 1-1, 2-1, 3-1, and so on would be created. The stern has a similar naming convention. However, the first number refers to its corresponding mid-body and the second to the sequential stern number. For mid-body 1, sterns 1-1, 1-2, 1-3, and so on would be created. This convention avoids confusion of model segments when multiple mid-bodies exist for the series. After the parent hull was validated and refined, geometric parameters were developed, and a naming convention devised, the 3 bow variants tested in this thesis were modeled. Similar to Kim's 1961 work on implicit bulbs, sectional area, defined as C sub AIB, was chosen as the varied parameter. A step size of 1.5% was selected to give a small initial step to avoid missing any trends in model test data for the varied parameter. The parent hull had a C sub AIB value of 8%, and the 1.5% step size gave subsequent bows of 9.5% and 11%. Note that the C sub HIB value was held constant for all 3 bows. Lastly, no modification to the parent hull stern was made as part of this thesis. I will now pass the presentation over to Tyler to discuss our model fabrication, test procedure, and results.
Thank you, John, for discussing the design and validation portion of this thesis. After defining both the parent model and bow variants, construction of the physical model could begin. Due to the complex curvature of the implicit bulbous bow and stern bulb, it was necessary to split the model into 3 main sections. As shown, these sections were then subdivided into another 3 sections to comply with the thickness of the foam provided. This resulted in 9 separate pieces overall to be cut. Following the first cut, some pieces were then adhered using alignment holes as shown above. This would allow each section to be cut as one continuous piece later on. Once each primary section was adhered, it was necessary to develop the toolpaths for the final model. Using the model was partitioned in Rhino 7, where each section was then uploaded to Fusion 360, a 3D modeling software. Using Fusion, both the roughing and final toolpaths were created for each model section. Shown on screen is the roughing toolpath for the starboard bow section, and after verification, each toolpath was exported to the shop app program for cutting. Shown here is the same starboard stern piece after both the roughing and final toolpaths were completed. It is important to note that the roughing cut is necessary to reduce excess foam, ensuring that the final pass is as accurate as possible. Once all the finishing cuts were completed, it was time to adhere the different sections together. As mentioned, the completed model was produced in 3 different sections: parallel mid-body, a bow, and a stern. These sections were kept separate to vary a bow and stern while reusing the same mid-body. And once each section was cut, each piece was coated with epoxy and sanded down multiple times. Following the epoxy coat, a white primer coat was applied twice and sanded down again, the final yellow coat then being applied at the end. When the coating for each section was completed, it became time to put together the full model. First, the model was aligned using the flatter bottom of the stern and bow. This would ensure the entire model was flush along baseline. Once aligned, the bow and stern sections were attached using 3 5-inch wood screws through a 1/4-inch backing plate. The bow and stern attached, the remaining gap between the sections was filled in with modeling clay, producing the parent model as seen right here. As mentioned, 2 additional valves were fabricated with estimations of 2-1 and 3-1, also shown right here, as well as on the screen. Now that manufacturing has concluded, we may move on to the testing procedure of the model. As with all resistance testing, a testing matrix must be defined to capture a range of vessel operating states. For our model, testing matrix includes a fold departure condition at a full-scale draft of 16 meters and a ballast arrival condition at a draft of 12 meters. The draft for the ballast arrival condition was selected, as it is the minimum draft where full propeller submersion still occurs. Under the fold departure condition, selected trims included even keel, 1 meter by the bow, and 1 meter by the stern. And under the ballast arrival condition, trims selected included even keel, 1 meter by the bow, and 3 meters by the stern. Finally, 4 speeds were selected to show the prevalence of slow steaming in the container industry. Speeds selected included full-scale operation at 14, 18, 22, and 26 knots. Given the different trim, draft, and speed conditions, 24 test cases in total were needed. And given that each speed needed to be run 3 times for validation, this bumps us up to 72 different tests per hull. Given we have 3 hulls, this means we have 216 tests to run. Moving over to model scale, the previously mentioned scale factor of 254.6 was used to convert the set ship conditions to model scale. Using Froude number scaling, the selected test speeds were then converted down to model scale. For reference, a Froude number of 0.117 corresponds to a ship speed of 14 knots, 0.15 to 18 knots, 0.183 to 22 knots, and 0.217 to 26 knots. It is important to note that all tested speeds are below the first peak in the CR Froude number plot. Before we go into the testing procedure, it is important to note the placement of HAMA strips on the vessel. HAMA strips, which are generally placed at the front of the model, are used to force the flow around the model transition from laminar to turbulent, matching the flow regime of the full-scale vessel. Per the Robinson model Basin procedure, our HAMA strips were created by layering electrical tape 4 layers thick and cutting them into triangular pattern. See that right here. Inducing turbulence as the fluid moves across the bow. For our model, a single row of HAMA strips were placed after the FP at 5% of the LBP. This ensures that the flow regime of the vessel matches the ITTC 1957 guidelines. However, initial testing produced resistance values that were lower than expected, especially at slower speeds. This led to the theory that the flow around the transition to mid-body was reattaching as laminar, which does not match the turbulent conditions as seen on the full-scale ship. Therefore, a second set of HAMA strips was added. Credit for this design choice belongs to Professor Hadler, who had experience working with models at low Froude numbers. Here's an example of one of the tests conducted at the full departure 0 trim condition at a speed of 1.9 feet per second. As mentioned, there were 72 separate runs to complete for each variation, and while it may seem daunting, we did make it happen. Following the conclusion of testing, it was then time to post-process to collect the data. In the interest of time, the remainder of this presentation will focus on the full departure condition at even keel. The figure on screen provides a measured resistance for each hull, where the x-axis is speed in feet per second, and the y-axis is measured resistance in pounds force. Between the measured speeds, measured resistance increased as speed increased, which was to be expected. Unfortunately, when examining the difference in resistance between the 3 variants, little distinction could be made. This is substantiated by the overlap between the 95% confidence intervals, where the difference in resistance between the hulls was less than 1/1000th of a pound force. Moving over to the residuary resistance coefficient, the figure on screen provides the results for each variant, where the x-axis represents Froude number and the y-axis is a non-dimensional coefficient. Similar to the previous plot, no identifiable trends could be recognized between the variants. That being said, residuary resistance only accounts for between 5 and 20% of the measured resistance at model scale, which is quite small when applied to the measured forces. The sinkage results are as follows, where the x-axis is speed in feet per second and the y-axis is sinkage in inches. Examining the results, it is clear that as speed increased, sinkage also increased, which was to be expected. However, once again, no identifiable trends could be recognized between the different hull forms. On a similar note, when examining trim results, where the x-axis represents speed in feet per second and the y-axis represents trim in degrees, no conclusive differences were recognized between the variants. Regardless, like the sinkage results, measured trim increased as speed increased. It is important to note that due to model constraints, the tow point of the vessel was above the designated shaft line, which produced a forward trimming moment, increasing the relative trim of the model. It is clear that the presented results contain a large variance, in which no conclusive observation can be made between each bow. However, it is clear that error in measurement was much higher for lower resistance values, as described by the plot on screen. While the direct cause of error cannot be determined, testing at low speeds, which causes an increase in relative noise compared to the average force value, may be to blame. Despite the uncertainty presented in the measured results, we can draw certain conclusions from the work today. First, as laid out in the objective, a characteristic ULCS hull form was created and tested, as well as 2 bow variants, which can serve as a parent model for future variations. Next, the CQ quality of the hull form was verified, which also lays the groundwork for future studies. Once the hull is validated, parameters were developed to describe both the stern bulb and implicit bulb, parameters which did not exist before this thesis. Finally, it is clear that the large-scale factor tested produced significant error, especially at low speeds, making it difficult to distinguish between the different bow variants. This brings me to our recommendations for future work. As mentioned, making a reasonably larger model of the hull form would both increase measurable differences between the bows, as well as increase the minimum speeds to test, reducing the noise that we saw at the lower speeds. Given this information, we believe a model of around 7 or 8 feet would provide better results while remaining within the constraints of the Robinson model basin. Another recommendation is continue varying the parent hull model characteristics, such as block coefficient, implicit bulb characteristics, stern bulb characteristics, and others to enlarge the developed database. Finally, it would be interesting to conduct a CFD analysis using variants of the parent hull to develop different characteristics to test in the Robinson model basin. Thank you for your time. I would now ask everybody to please hold their questions until the end, as I invite up Burke and Dan to present their thesis.